Okay, so I'm going to quickly review this chapter again. We're talking about electric currents. Electric currents are when charges are, you have an electric current when charges move. Okay. The previous 4 chapters that we studied, we studied properties of charges, but they were at rest. So now we're going to get them to move. Okay. So we'll study currents, and then in the next chapter we'll study direct current circuits. We will learn that magnetic fields are produced by currents. Okay? Magnetic fields will be produced by moving charges. Again, we mentioned these are Maxwell's 4 equations that describe all classical electromagnetic phenomena. Okay? So these are Maxwell's equation in differential equation form. And these are the same equations in integral form. Again, you don't have to know this. I'm just giving you extra information. It's electrical engineering is mainly based on these 4 equations. Okay, and the way these equations are structured is, on the right-hand side, you have sources producing these fields. Okay. And then you saw that once you produce these fields, if you want to detect them, so for instance, charges produce electric fields, and if you want to detect these fields, this electric field, you need a charge. A charge will produce a field, and to detect that field, you need a charge. A moving charge will produce a magnetic field, and to detect a magnetic field, you need a moving charge. Okay. So you saw all of that. So for instance, we'll study a full chapter on just this part of the equation. Okay. So this equation tells you current densities. Currents produce magnetic fields. So for instance, what this equation is telling you is, if you have an infinitely long conductor like this, it'll produce magnetic fields that are concentric circles. So magnetic fields will be like that. Okay, so that's what this equation is telling you, among other things. Okay, and so on. All right, so you saw this here. There's a battery connected to a bulb. The switch is not closed and it's not lit. So when you close the switch, it lights up. And most devices in your life, your appliances, they don't care which way the current flows. Okay, a bulb certainly doesn't care which way the current flows. Okay. All right, so we saw all of that. Now what this diagram is showing you is, so in a metal, each atom is fixed, and those fixed atoms let go of a couple of their outermost electrons. Okay? And these electrons act like a free gas. Okay, so for instance, there's about 10 to the power of 28 particles, gas molecules in this room, and there's that many free electrons in this faucet. Okay, so those free electrons act like this gas molecules. Now, when this metal is not connected to a battery, these guys just move around randomly, and they bounce into these ions. So these electrons are moving about very fast randomly. They're in fact moving at about 1,000 kilometers a second. They'll go from here to Atlanta in 1 second. But if you paint this guy blue, you come back 3 years later, he'll still be here on the average. Now, if you connect this piece of metal to a battery, that battery creates an electric field. And once there's an electric field in the metal, these guys will move opposite to the electric field. The electrons drift opposite to the electric field. Anybody remember what the drift velocity is on the average? I'm sorry?
2 millimeters.
Yeah, about a millimeter a second, yeah. Okay. So you guys understand, on top of 1,000 kilometers a second is superimposed a millimeter a second. Okay. So that's a billionth of a speed. Okay. So there's an average background speed of 1,000 kilometers a second. 1,000, that's 10 to the power 6 meters a second, and a millimeter is 10 to the minus 3 meters. So a billionth of that speed is the drift velocity. Okay. You saw that an electron will collide with an atom on the average 10 to the minus 15 seconds later. 10 to the minus 15 is a femtosecond, 10 femtoseconds later, and so on. Okay, so in a conductor, normally, if it's not connected to a battery, the current electric field is 0. When you connect it to a battery, the battery establishes a electric field in the conductor, and now the charge is moving in response to the electric field. Okay, so that's what happens. You guys remember that? Yeah. So the drift speed is, so here's an electron inside a metal, and here it's moving randomly. This, each time it changes direction, it's bounced off an ion. You can think of it that way. Okay. And when you establish an electric field in this metal wire, how do you establish this electric field? By connecting a battery. Okay. So once you connect a battery to the wire, then, so this is, the electrons will drift in that direction. Okay, and this is about a millimeter a second. Okay, so that's the complicated thing that's going on. Okay. Now, so what is the difference between this diagram and this diagram?
Twice the
Hmm?
amount. You have twice the amount of energy.
The voltage applied is twice as much. And so here's Ohm's law. If you double the voltage, the current doubles in that resistance. Okay? So here's what's happened. How did the current double? Okay, so you come back to this. When you double the voltage, the electric field doubles and the drift velocity doubles, and that's when the current doubles. So if for 3 volts it was going at 1 millimeter a second, if you apply 6 volts, what's happening? Very good. Okay, it's going at 2 millimeters. That's what's happening. All right, so again, like I said, drift velocity is about a millimeter a second. And then we mentioned, so if you have a electrical circuit, the instant you close the switch, the light seems to go on. What happens is, when you close the switch, okay, so the question was, if the drift speed are so small, why does the light bulb go on almost immediately after closing the switch? When you close the switch, the electric field is established at the speed of light. And soon as the electric field is on, the electrons at that location start drifting. And so the light will go on. All right, so let me ask you a puzzle. Let's do a puzzle. So imagine the following. This is the sun. Here's the earth. Now let's assume that the sun gets turned on by you closing a switch. So you're powering it with a battery. Okay, so now you close the switch. How long does it take for the sun to go on?
It
All right.
So,
How fast is the electric field getting switched on? Speed of light. I'm sorry?
Is it the drift speed?
No, the electric field is getting turned on at the speed of light. So what happens is you close the switch, the electric field gets turned on at the speed of light, and the electric field gets to the sun 8 minutes later. As soon as the electric field gets turned on, electrons start flowing, and then it takes another 8 minutes for the light to get to you. So for the sun, if you close the switch, unlike this light switch, you'll see light 16 minutes later. All right. Did you guys understand that? All right. All right. Anyway, so the thing is, electrons will an electron here responds to the electric field right there. It doesn't care what is happening anywhere else. Okay, a particle will respond to a field right at its location. Okay, so as soon as an electric field gets turned on and it's at its location, it'll respond to that. Okay. All right, so electric currents are denoted by I. And so here's a wire, and the electric current tells you how much charge is flowing across that point per second. Okay, and that's what the electric current is. So this is the rate of flow of charge. Charge is measured in coulombs, time in seconds. So this combination of units is called an ampere. Okay, so an ampere is the SI unit for current. Okay. Here are some typical currents in your life. So again, when a neuron fires, it's a billionth of a ampere, and we'll look at the details of this in one of the next chapters. Okay. Your 100-watt light bulb carries a 1 amp current. Okay. A lightning is 10,000 amps. Okay. A lightning bolt carries 10,000 amps, and so on. The aurora is 1,000,000 amps. Okay. Right, so now by convention, here's a battery. The long line is the positive terminal of the battery. The short line is the negative terminal. And by convention, current flows from the positive to negative terminal. Okay? But in a metal, really, it's electrons flowing in the opposite direction. Okay? So this convention was adopted before we knew about electrons. So this is showing an electrolyte, for instance, which has both positive and negative charges, free charges. Okay. And this is okay. Also in a solar plasma, in the sun's atmosphere, you have plasma where both positive and negative charges exist, and they both will carry currents. In a conductor, it's only electrons that carry current. Okay. So in this metal wire, which way are the electrons flowing? Opposite to the direction of the current. Yeah. Okay. I'm going fast because I'm just reviewing this stuff, okay? I'm just reminding you of. Okay, so in the microscopic model of current, so let's say this is a metal wire. It's electrons that carry current. The current is flowing in the direction positive charges would flow. So here are the electrons drifting, and this drift speed is about 1 millimeter a second. Okay? And the current is given by the electron charge density, free electron charge density. Okay, how many electrons can participate in current? Okay, and this number can be about N is of the order of 10 to the 28 per meter cube. So meter cube is that computer desk, that volume, and in that large a metal piece, there will be about 10 to the power of 28 free electrons. Okay? So that's what that number means. If electrons are a charge carrier, that's the charge of the electron. That's the drift speed, about 1 millimeter a second, and the A is the area of cross-section of the wire. Okay? Okay, so when the current doubles in a wire, what has happened? The number of charges can't change, the charge of the electron doesn't change, the area cross section of the wire doesn't change, so the only thing that changes is the drift speed. You double the current, you double the drift speed. How did you double the drift speed? By doubling the electric field. Okay. By doubling the electric field, you can double the drift speed. And how do you double this? By doubling the voltage applied. Okay. All right. So here's a wire carrying a current. Here's the electric field in the wire. Okay, it turns out that, okay, so we define current density. Current density is the current flowing in the wire divided by the area of cross section of the wire. It turns out that this quantity is proportional to that. The current density is proportional to the electric field. Okay, so that's why we define that. Okay, so current density is proportional to the electric field, and that's Ohm's law. Okay. The proportionality constant is called the conductivity of the material. So for instance, with the same electric field in silver versus, let's say, a piece of rubber, silver is much better conductor, so the current density would be much higher. Okay. Rubber is a good insulator, so the current will almost be zero. Okay, so the current density is proportional to the electric field. Okay. So this battery established an electric field in this wire, and current density, current divided by area, is proportional to that. You double the voltage, you double the electric field, you double the current density, and you double the current. Okay, now this is Ohm's law, but it's hard to measure the electric field in that, okay, with the instruments that you have in lab. So what we'll do is we'll write this in the form, in a more useful form. Okay, you can measure current, not current density, and you can measure voltage, not electric fields. So what we'll do is, so there's current density is I over area, okay, and E times the length gives you the voltage across the wire. Okay, so this is voltage divided by length. Okay, so I is sigma A over L. And so V over okay, so the current in the wire is written in terms of the voltage across the wire times this quantity. Now this is easy to measure and this is easy to measure. Okay, so we are going to write Ohm's law in terms of that, and this guy is called the resistance. This guy is called the resistance of the wire. So your Ohm's law in terms of quantities that are easily measured is this. Okay, current is voltage divided by R. Okay. So current is voltage divided by R, or voltage is current times R, I times R. Okay. So this is the more useful form of Ohm's law. So the resistance of a wire depends on the length of the wire and inversely proportional to the area of cross-section of the wire. So for a given material, thicker wires have lower resistance, longer wires have higher resistance. Okay. Okay, you saw that water flows downhill, just like that. Positive charges flow in the direction of decreasing voltage. So what a battery does is establishes a voltage hill. when you connect a battery to a resistor, it makes this point at a higher potential and that's at a lower potential. And so positive charges would flow downhill like that. Okay. Now we mentioned this, so here's a positive charge, it's flowing downhill, it comes to the bottom. Now it's come to the bottom of the hill. Now what?
You need to apply water and get it back up.
Yeah, so you use some of the chemical energy stored in the battery to pick this positive charge and put it on top of the hill again. You use the chemical energy to pump it up, and then it can flow again. Okay. How long can you keep doing this? I'm sorry?
So you expend all chemical energy?
Yeah, till you have spent all your balance, bank balance. Okay. All right, you saw this color, these are all resistors, and the color coding tells you the value of the resistance, okay? And so, for instance, yeah, okay, let's read this one again. The first band is 2, so the first two bands tell you the first two digits, and the third band tells you what power of 10 you multiply it with. So this is 2. The first band is red is 2. The second band is black is 0. Okay. And the third band is brown is 1. And that's the third band tells you the power of 10 you'll multiply it with. Okay, so this is 200 ohms. And the last band, which is either a gold, silver, or colorless, tells you the accuracy of this value. The gold is 5%. 5% of that is 10 ohms, so plus or minus 10 ohms. That's what those colored bands are telling you. They're telling you the value of the resistor and the error. Okay. So if that gold band wasn't there, or if it was a colorless band, the error would be 20%. That would be plus or minus 40 ohms. Okay. All right, so you saw all of that. All right, so what is this battery? The battery is a store of energy, okay? So this is the source, this is called the load. What is this guy? I'm sorry? It's a load, it can be anything. It can be toaster, it can be your washing machine, it can be a fridge, it can be your Tesla car, or whatever, okay? So this is the source, and it delivers energy, and so the rate at which it delivers energy is given by power. Okay, so if it's providing a current I at voltage V, that's the rate at which it's delivering power. And then what's happening to this that energy here? This load is converting it into light, heat, or whatever it is that you're trying to do. So a light bulb converts that energy to light and so on. Okay, so the rate at which energy is power energy is delivered to the load is I square R. Okay, I is the current flowing in, and that's also equal to the rate at which the power is being delivered, or V times I. Okay, so the rate at which power is delivered to the load can be calculated one of these three formulas. Okay, so V is the voltage across the load, R is the resistance of the load, and so on. And one of the last things we saw was in the US, the grid is, and in most part of the world, there are some central power generating stations. And in the US, for instance, you can get electricity from the Hoover Dam, and that's 2,000 miles away. Okay. So what this is showing you is the power being sent by Hoover Dam. This is the power lost in the transmission lines, and that is load is what's in your house. So that's the power reaching your house. So this is I square R transmission plus I square R load. Okay, so you want to minimize this power loss in the transmission. Okay, so the easiest way to do that is to decrease the value of the current. Okay, now to decrease the value of the current, so this is the power that the Hoover dam is sending. So if you want to decrease the value of the current, you have to send the power at high voltage. Okay, and so transmission lines carry power at high voltage because they want to carry the power at low currents, so the transmission losses are minimized. Okay. You saw that diodes are sort of gateways. Okay, so here's a diode, and a diode will only let a current in this direction if this end is connected to a positive, this end is positive voltage and this end is negative voltage. Yeah. And here's a diagram for the current response of a diode. See, so here's a diode. Even if the positive voltage is 0.5 volts, that gate is not open yet. That gate opens when the voltage reaches 0.7 volts. So when you apply a 0.7 volts, then the gate opens, and then it's as if the diode is not even there. Okay? If you apply a negative voltage to that point, that gate is shut. It won't let any current through that way. Okay, so a diode is a one-way gate for a current. Okay? So in a circuit, if you want to make sure that you want current flowing only in this direction, you just put a diode in there. You saw that a thermistor is a material whose resistance changes dramatically with temperature. And you can use these devices to measure temperatures. Okay? For an ordinary piece of metal like copper and stuff like that, its resistance increases linearly with temperature. Okay? This is the graph for a semiconductor. This is the resistivity, also the resistance. As you increase the temperature, what happens is, so here's a band structure. As you increase the temperature, the free charge carriers increase. More charges are excited from the valence band to the conduction band, and its conductivity increases and its resistivity decreases. So as you increase the temperature of a semiconductor, it conducts electricity better. Okay, that's what this graph is telling you. Okay. Copper wire, on the other hand, as you increase the temperature, its resistance increases, not decreases. Its resistance increases and the current flows down. Okay? All right, so this is the point where we stopped at last time. Okay, so there are some materials where if you decrease their temperature below a critical temperature, the resistance goes to 0. All right, so here was Ohm's law. Well, what happens if resistance goes to 0? Then you don't need a voltage to pass a current. Okay, so in such wires, okay, so here's a battery, and this, now the wire is above the critical temperature. You pass a current through it, and then what you do is you start cooling it down. So decrease the temperature, and once the temperature goes below critical temperature, you can remove the battery and the current will still keep flowing. Okay. All right, so this is superconductivity, okay, when the resistance goes to 0. It was first discovered in mercury in 1911. Okay. So 1911 is once superconductivity was discovered in mercury. Okay. And for the longest time, the critical temperature was very cold, up to 30 degree Kelvin. What is the critical temperature again? That's the temperature below you have to cool this, below which you have to cool the sample to make it superconducting. Yes. What you want is some material to become superconducting at room temperature. That would be, I mean, you could become a billionaire if you can come up with that. So we were looking for temperature higher and higher temperatures for the longest time. And you see, we got nowhere for about 70 years. And then suddenly they found materials, they started looking at materials that they had not looked at before, and the critical temperatures shot up. Yeah. This is a very important temperature. Liquid nitrogen, that's 77 degree Kelvin. Okay. And the reason being, so if you want to cool something to this temperature, you have to use liquid helium, which is expensive. Liquid nitrogen is cheap. So anything with critical temperature above that, now that you can use it cheaply. So all your MRI machines, they use materials with liquid nitrogen as a coolant. I don't know what the prices are now, but liquid helium used to be $2 a liter. Liquid nitrogen is about 10 cents a liter. Okay. So you see how much cheaper these guys are to operate. Okay. Now here's one of the applications of superconductors. Okay. You'll see that in the next chapter, if you have a current flowing like this behaves like a magnet. Okay. So stick your right hand fingers in the direction of the current, and this is the direction in which the magnet points. Okay. So you can, oops. So the idea is the following. You can have a current, supercurrent flowing in a train like this, which now behaves like a magnet. I'm just drawing a very simple picture. And if the track has a magnet magnetized like that, what will happen? This will repel it, and this train can float. And then all we have to do is get Brock to push this, and this train will go all the way to DC.
Maglev.
Huh? Maglev. Have you been on a maglev train? No. Anybody been on a maglev train? You haven't gone to China? Shanghai? Mm.
Have you?
No, I'd like to.
Let's go.
Well, you go to Bali all the time, so you're not too far from Shanghai.
Yeah. Might try to stop there next time.
Yep. Yeah, do that. So there's a maglev train from Shanghai airport to the city, 40 kilometers long. Yep. And so you can make sure that you get it as part of your ticket.
Yeah.
Okay, so let's watch this one.
One doesn't have to be a passionate fan of model trains to be fascinated by the way this steam engine looks. Hovering a few millimeters over the rails, it goes round and round without any friction and without any motor. On top of that, it really steams. But it's not water that evaporates inside the model steam engine, but liquid nitrogen, so cold that humidity condenses on it. The core of this magnetic levitation train is a superconducting material which conducts electric current without any resistance at temperatures below minus 183 degrees Celsius. In this state, it's able to trap magnetic fields. The resulting magnetic forces cause not only the levitation, but precision control above the rail, which is made of conventional magnetic material. An impressive experiment is designed to demonstrate how strong the forces are which hold the superconductor on the track. The superconductor is brought into a certain distance of a few millimeters above the magnetic rail and cooled down in this position using liquid nitrogen. Reaching the specific transition temperature of minus 183 degrees Celsius, the superconductor traps the magnetic flux of the outer field. Now we can remove the shim of a certain thickness which determines the distance. The superconductor has now memorized its position within the field of the rail. The superconductor is fixed at this distance and can only move along the magnetic rail even when turning upside down. But the effect lasts only as long as the superconducting state in the material is maintained. To set the superconducting levitation train in motion, one has only to give it an initial impulse by hand. Due to the lack of friction, the steam engine goes round and round until the liquid nitrogen is evaporated and the material warms up. Then the effect of superconductivity ceases, and what has been a strong magnet at low temperatures turns into a ceramic material without particular magnetic properties. Above the so-called transition temperature, superconductors are no longer affected by magnetic fields, and the locomotive drops back to the rail due to the effects of gravity.
So you saw that soon as the temperature rose above the critical temperature, now it's become an ordinary conductor and the current dies. Okay. So maglev trains operate on that principle, and Shanghai train has been in operation since 2004. So the Shanghai train, it's a 40-kilometer ride, and what it does is, so here's 20 kilometers, it's speeding up to there and then it's braking. And the peak speed is, I believe, about 250 miles per hour. Okay. All right, so we will stop here. Well, okay, so the Drude model just tells you, okay, again, we talked about this, see the electrons, when no electric fields are, this is inside a metal wire, these guys are moving about randomly at about 1,000 kilometers a second, but they're not going anywhere. As soon as you turn on an electric field, by connecting a battery, now they acquire a drift speed of about 1 millimeter a second. Okay? And so, anyways, so that's, and the average velocity is the drift velocity, which is given by that. That's the time between collisions, average mean so mean time between collisions, and that's the electric field, that's the mass of the electron. Okay. All right, we will stop here.